So changing gears now that we've gone into the nitty-gritty of power measurement, let's look at some system level aircraft architectures and how we might test those. So let's say we have a quadcopter, one of those little toy aircrafts or drones that deliver our packages. And we want to do a system level test on this. Well, we're going to want to look at individual inverter efficiency as well as some system control type things. And we're going to want to understand the total system efficiency. So what the eDrive system has implemented is what we call an eDrive creator. It's actually a really cool way where you can more or less drag and drop blocks to create your own individual powertrain. So we drag a DC bus box over. This is our battery. We drag a three-phase inverter for each of our 4 motors because they're quadcopter. And we can look at the total system efficiency. That's my box in green here, and our individual efficiencies. What this is actually doing is setting up the efficiency and power equations in the real-time formulas so that it's transparent to you. This is really beneficial when you're going out and you're testing supplier parts, or you're running a test for a customer, and the customer's at your desk and they say, "How is my part doing?" And you can bring up this display and you say, "Well, this is our test, and your part is the front nose inverter," and you double click on that, and you can start to see displays, traces, and maps of the individual component. Again, we're doing all these calculations in real time. We're doing, in this example, 3, 6, 9, 12 phases of power measurement, well, 13 with the DC bus, and looking at the system level efficiency. And if we take that test and we extrapolate to what it really is, we have a load cell. We have our quadcopter. It was much bigger than this, but take my animation for what it is. And we click on that component and we say we want to visualize this. So we go from our setup, we click on our component, and we go into viewing our measurement. And again, in my traces, I have a blue trace for the voltage of each one of my motors. So we have the nose starboard, nose port, aft starboard, aft port motors. And in this instance, the aft starboard motor had failed, so this was a little bit of a control test. Could I take off with 3 motors? And we were looking at the load and what's the angle of the load. So we can see the voltage and current for each motor. We can see dynamics in a couple of them. This was a 30-second test looking at the lift created by the 3 motors. Each measurement was recorded at 2 megasamples per second. And we were looking at the load, or the up force of the entire vehicle, and visualizing all of those in the real time. So it was a really cool test because we were looking at the total system control. How does each motor want to perform in this failure event of losing a motor? And we used a 6-axis load cell, so you can actually look at FX, FY, FZ, and then the moments. I'm only going to show one axis in my, that'll be in a later slide. I apologize. So if we look at the electromechanical aircraft tests, we can start bringing in things like those load cells and those vibrations. So again, my example of my fan motor with my load cell. I thought I had data on that last one. I chose not to show it, but this is a different test that's very similar. So this is a deep sea propeller motor startup. So this would be a much more simple motor where we're recording voltage and current, DC voltage and current, thrust, and then vibration, because we wanted to look at what is the vibration of this motor out on a lever arm. If we think of the quadcopter again, the motor's out at a distance on a lever. So we start up this motor, and we can see the voltage and current increase, and the load increases with the current. And there's a little bit of a phase delay in that, as we would expect. And then as that load is increasing, our vibration is also increasing. So we can see that, as we're starting up, as we're really putting a bunch of current into this machine, we get a ton of vibration. And this is just the motor shaking out at the end of the propeller. Then as we decrease the load and we go into more of a steady state operation, we can see that that vibration chills out and it goes down pretty significantly. What this allows us to do is start running things like NVH analysis, looking at how our currents sampled at a very high rate actually influence our vibrations, which are also sampled at a high rate, and start to correlate the transference from current to vibration. We can see that vibration increases with speed of the machine, but it's really unique being able to look at these two values, high frequency current as well as high frequency vibration on the same timestamp, and start to analyze resonances and start to understand these complex systems. The systems we've implemented with some of our electric aircraft partners have almost all had a high number of accelerometer channels for understanding the vibration of the system. It's unbelievably important to durability, fatigue, as well as the experience of the vehicle. Endurance testing. This is a fairly boring test, but a very important test. So this was looking at total energy used over a long period of electric aircraft. So basically, they hooked up some clamps to the DC bus of an inverter. They were looking at average current, average power, and total energy used over a period, and they were looking for dropout events, faults, blah blah blah, and they were doing it over a period of weeks. Then, if an event were to happen, they would have a trigger and take some really high-speed data. So with these long-term testing, because we're doing those calculations in the real time, we're able to stream them out over CAN bus or EtherCAT to an automation system. And that automation system could just record that slow rate data. We can record that slow rate data. But then if an event happens, you can have a trigger and take that very high-speed data, that 2 megasample data, and have a buffer where you can know 10 minutes before my failure, 10 minutes after my failure, or you could just have a slow stream of data and understand a 10-week test, a 10-hour test in its entirety. So nothing too exciting, but these long endurance tests and having a proper amount of data and understanding failures and having data for failures can be very important. Now, it'd be a shame if I neglected all the other elements of aircraft that are electrifying. So if we think about things like actuators, I've presented on this topic before, but this is an electric actuator test where there was 2 electric actuators, so 1, 2, each of them being a 3-phase machine, a load cell for each, a load cell for the load. So we have 3 load cells, 6 power measurements. We have accelerometers, displacement sensors, and we're really looking at a wide variety of things. With the number of measurements in the system, reducing instrumentation complexity was extremely important to the customer. Reducing instrumentation cost, if you have 8 different boxes for this type of test, it raises your cost significantly rather than just having one. They wanted to look at efficiency, but also control of these electric actuators. And temperature was one of the very big variables for them. But if we think about this complex system where we have electric power measurement coming into the Genesis system, displacement measurements coming into the Genesis system, accelerometers, load cells, temperatures, that's a lot of information. And if you have it coming into one system with one data file, you can timeline all of that data, really have confidence that one phenomena is related to another. We just have confidence that this is how our test is operating. This is the best way our test can be operating.